So today we're going to learn about rational exponents. So what is a rational exponent? It's pretty much an exponent form. So you have the base, you have the exponent, and the exponent is in the form of a fraction. In other words, an example could be, for example, 4 to the power of 3 over 5. So here you have the base, here you have the exponent, but the exponent is in a fraction rational form. So you have been indirectly working with rational exponents. For example, let's just say you did 4 to the power of 2. Well, we know from grade 9 or grade 8 or whatever, this is the same thing as 4 times 4. But what you don't see is that this exponent is actually over 1. So in your junior years, all your exponents have been in the fraction form, but you just don't realize it is actually over 1. So the 1 doesn't really do much to the overall effect of the exponent. So now in the following table, we're going to investigate, well, what happens when you have a number that is not a 1 in the denominator of your exponent. So we're going to let the exponent be 1 over something, 1 over something. So I'd like for everyone to stop the video if you can and actually enter this into your calculator. In other words, you're going to use your exponent button on your calculator, which is y over x, or it could be a little pointy thing, or maybe it depends on your calculator. So when you type this in your calculator, 4 to the power of whatever that button is, and in bracket 1 divided by 2. So make sure you have put a bracket when you do the exponent part. So on the right hand side, when you take 4 to the power of half, you get 2, 9 to the power of half, 3, 5, and 10. So what we're going to do right now is have a look at the connection between the 4 and the 2. The base 9, and you got a 3. 25, something, exponent gives you 5. How is 100 related to 10? And you might realize that it seems like 4 here is the square root of 4 will give you 2. 9, the square root of 9 will give you 3. 25, the square root of 25 will give you 5. And 100, the square root of 100 will give you 10. Now, how is the exponent over here, the 2, these little 2's here, related to the square root? Well, remember what square root means? Square root means you need to find two numbers that multiply, the same numbers that multiply to give you 4. Two numbers. So in other words, this little 2 means find me two numbers. I'll put here a bit more clear. Find me two numbers that will give me 9, and these two numbers have to be the same. So if I were to do the following, let's do a 36 to the power of half. Well, what this really means is give me two numbers, or give me two numbers that will multiply to give me 36 twice. So something times something will give me 36, which are the same. In this case, is going to be 6. So what I'm trying to say in this particular example is that this half here, this little 2, actually tells you the square root of the base. So let's do a similar example, but now instead of having 2 in the denominator, we have a 3. So what does this mean? So let's try without using your calculators. So what this means is give me a number when multiply 3 times, for example, something times something times something, and these somethings have to be the same 3 times, will give you 8. And what is that number going to be? Well, that number is going to be 2. And if you're not convinced, you can actually put this in your calculator. It will give you a 2. Same thing for here. This means to find not the square root, but it's actually the cube root. The cube root. So give me a number that multiplies 3 times. They have to be the same. That will give you 27, and that number is going to be 3. Same thing for here. This is going to give you 5, and this is going to give you 10. So on your calculator, you actually have a button that looks like this. So what this means is, this little x means the type of root, the type of root. Now, if you were to type this in your calculator using, we call this the radical form, this here is the same thing as 8, and this little 3 here, over here, tells you the type of root that you're looking for. Now, going back to the previous example, if I asked you for 4 1/2, this is the same thing as the square root of 4. Now, technically you don't have to put a 2 here. By default, if someone wrote down just square root of 4, so this 4, it automatically means 2. However, someone can put, for example, 4 and 3. Well, this means you kind of take this cube root of 4, and I think you have this button on your calculator, and that should give you some sort of decimal. So in the blank row here, if I say 64 to the power of 1 over 3, it is exactly the same thing as 64. But in this case, you need to put the little 3 because you want to take because the fraction indicates, the denominator indicates that you want to take the cube root. And if you put this in your calculator, whichever way, you can use your exponent button or you can use your radical button, and you end up getting a 4. And that makes sense because 4 times 4 times 4, 3 times will give you 64. So now let's just generalize this statement. So if we have a base to the power of a fraction, 1 over n, this can actually, so this form is called exponent form because you have a base and an exponent. And this can be written as a radical form. So this symbol I'm writing is a radical form, and with a little n inside, that tells you the type of root you're looking for. And the radicand is the b. So this b is called the radicand. This symbol here, in grade 9 or 10, you call it a square root, but we can't call it a square root because this inside here is not necessarily a 2, could be any number that's greater than a 2, and that is called the radicand. And this is overall called the radical form. So if I were to change this question, and let's just say I said 16 to the 1 over 4. Well, you don't really need a calculator for this if you're comfortable with your multiplication skills. So what this means is, okay, this is the same thing as the 4th root of 16. When I say 4th root, you need to find me a number that when you multiply 4 times, that will give you 16. And what is that number going to be? And that number is going to be a 2. So the next thing we're going to talk about is, well, what happens if you have negative numbers inside the radical? What happens? Well, this is where you have to take precaution. And we'll talk about that in the next slide. So in this first example, square root of negative 25, you need to find me 2 numbers that multiply which are the same. That will give you negative 25. Some student might say, well, 5 times 5. That doesn't work because it gives you a positive 25. What about negative 5 times negative 5? Because keep in mind these 2 numbers have to be the same. Well, it still gives you positive 25. So the idea is there is no way you can get 2 numbers that are the same that will give you a negative number. So in other words, this number does not exist. So you got to be careful of the types of numbers inside the radicals. So if I were to express this in terms of a exponent form, keep in mind you need to put a bracket, negative 25, indicating that the whole entire base is negative 25. In this case, there's a little 2 here because it's a square root. You don't see the 2, but it's automatically a 2 if you don't see a number inside this area here. And that becomes 1 over 2. And when you put this in your calculator, you get a does not exist. And since we're talking about negatives, there's a difference between the following 2 forms. So let me just write the following. Negative 25 and a half without a bracket versus negative 25 with a bracket to the half. There is a big difference. So when you have the right-hand side, it's the same thing as the square root of everything inside, which is negative 25 square root. I don't need to put a 2, but I'm just showing you that this denominator is connected to the 2 here. It's a square root. Now over here, this one over here. Now the base is not negative 25. That's because without a bracket, this is assumed that there's actually a negative 1 in front. So this is a negative 1. In other words, this is the same thing as negative 1 times 25 and a half. So in other words, the true base is actually 25. So when you put this into a radical form, there's a negative 1 times, then you can put the square root of 25. And you end up getting a number, negative 5, because this piece gives you a 5 and you multiply by negative 1. So there's a difference between brackets and no brackets with a negative in front. Well, what happens if you have a bracket negative 8? Well, just because you have a bracket negative 8, it doesn't mean that you cannot get an answer, unlike the previous question. You have to look at the type of root you're talking about. So in this case, if I change it to a radical form, you get negative 8 inside as a radicand, and the 3 means you're taking the cube root. All right. So in other words, when you put this in your calculator, you get an actual real number, which is a negative 2. Well, why is that? Well, because negative 2 times negative 2 times negative 2, 3 times, will give you the negative 8. So there is a connection between negative bases and the type of denominator number. So when it comes to, for example, let's do another one. Let's do negative 16. And let's, instead of having a 3, let's increase it to 4. So this is the same thing as the radical. Inside is negative 16. And this 4 tells you the type of root, fourth root. This is asking you, find me 4 numbers that are the same that will give you negative 16. Well, you only have 2 choices. Either it's 2, 2, 2, 2, but if you multiply 2 4 times, you're going to end up with a positive 16, which we don't want. We want a negative 16. If you do the same thing for all, if you make the all negative 2's, you also end up getting positive 16. So there's something about multiplying negative numbers even number of times that will always give you a positive. So in other words, this does not exist because there's no way you can get a number that multiplies to give you a negative 16 even number of times. So when it comes to, just to generalize a rule, if you'd like to know about this, when it comes to negative radicals, so if you have a negative number inside here and inside here is a even root, you're going to end up getting does not exist. However, if you have a negative number inside the radical and you have an odd number, you're going to get some sort of answer, because it's the way that the signs work when it comes to multiplying negatives x number of times. So if you multiply a number odd number of times, you're going to get a negative number. But if you multiply a negative number even number of times, you're going to get a positive number. So just be aware of the signs. And just to add on, well, miss, what happens if you don't put a bracket for this example here? Well, as I said before, the base is not negative 16, it's actually negative 1 times 16, 1 over 4. In other words, the base is actually 16. So when you actually put this into radical form, you get negative 1 times the fourth root of 16, and you do this part here first, and you end up getting 2, which gives you negative 2. So there's a difference between this format and this format, with a bracket negative base versus no brackets. So far we've been focusing on b to the power of 1 over n, where n tells you the type of root. So this is your nth root. So what happens if you include a number on the top instead of having a 1 in the numerator? Well, what's going to happen is the following. So let's actually look at this 2 over 1. So here we have a rational exponent-ish. Now the only difference is this 2 tells you the number of times to multiply 4. Now the 1, there's no such thing as a 1th root. The 1 makes no difference. This actually means 4 times 4 because the top number, numerator, tells you the number of times to multiply the base by. So let's include 4 2 over 3. Now what does that mean? Well, there's a couple of ways you can approach this. You can separate the exponents, break it up, meaning we can have 2 bracket 1 over 3. So I'm actually using the power law to work backwards. Or I can express this as 4 1 over 3 times 2. It really depends on which one you're going to do. Now what does this become? Well, we know that this thing here tells you the third root. So that's why we put a 3 inside here. And what goes inside here in the radical? Well, 4 to the power of 2. Or if you take it from this point of view, all right, this here directly becomes the radical 4 with the third root, but outside, I'll put a brackets outside, you have a square. So there's 2 ways to look at this. So if I were to take this and generalize this, so we'll hear bm over n is the same thing as bm to the power of 1 over n, or you could do the reverse, the other way around. And if I were to change this to a radical form, this is the same thing as, so this whole thing is to the nth root. So the nth root goes over here. What goes inside the radical is the radicand. Or we can do it this way, where we can deal with the base. This tells you the type of root. And outside, you take the power of m. So these are 2 formats that are the same. It just depends on where you want the brackets or not. So what happens when we have negative rational exponents? So in this case, well, what happens if I have, for example, 4 to the power of negative 5 over 4? What does this really mean? How can we sort of rewrite this as a radical form? One thing first is, well, if you recall from the last video, what does negative exponents mean? That negative in front. Well, it actually means you're going to take the reciprocal. In other words, this becomes 1 over, and then after that, in the denominator, you just keep the base and exponent, which is 4 and 5 over 4. You don't have the negative because we already dealt with the reciprocal already. And then you're pretty much done, meaning you can actually take the denominator and now change it into a radical form. In this case, it would be, what kind of root is it? It's going to be the fourth root with the base being 4, and then the exponent is on the 5. Or if you want to rewrite it as bracket 5 on the outside, it is up to you. So having a negative exponent doesn't make the question more difficult. It's just you may have a fraction, or you may need to take the reciprocal. So I just want to address two little things. Number one is the way that you write a radical form. So if you notice up here, you can see the little 4s inside the little, I'll call it the little check mark here. But if you look at here, the way that I wrote this, it's the way that I wrote it, it's kind of hard to tell whether it is the following. Are you talking about this, miss? Or are you talking about this? So when it comes to writing the nth root or the 4th root or the 5th root, just make sure that that little 4 is inside that little check marky thing here and not like this. There's a difference between the two. Number 2 is your calculator. Does everyone here know how to use this button on their calculator? As I said, every calculator has a different way to calculate the nth root. So if everyone here can do the following, for example, can you type in 3 and root 8? Will it give you 2? So hopefully that you will get a 2. If you do get a 2, that means your calculator is working. Or if you do the following, can you do the following? Will that give you a 4? If it does, that means you know how to work with your calculator. If not, then please email me and I will address it right away. And to add on a third thing, based on my personal experience with calculators, some calculators cannot do this. They may not be able to handle negative rational exponents. So in this case, you may have to actually change it into a positive rational, meaning you have to take the reciprocal, and then your calculator should be able to handle it. As I said, I don't know which calculators do, but I have encountered where some calculators cannot manage some of these calculations. So right now, let's actually go over some examples. So in this case, you have everything in a base and exponents. Here's your base, exponent, base, exponent, base, exponent. And the question is, can you change it to a radical form? And then if so, can you use your calculator? Well, actually, without using your calculator. Okay, so over here, first things first, let's change this to a radical. So here's a radical, and the base is a 27. This bottom number here, it tells you the nth root, so make sure that 3 is very, very small inside that little tick checky mark. And then the 2 can be directly on the 27. And then over here to the right, you can actually do the same thing. It's pretty much the same thing. So this entire thing is in brackets. That means the base is negative 27, and you have the 3 and the 2. So next thing is, without using a calculator, evaluate. So there's a couple of ways to do this. For me personally, this is where I think changing bases would be fine if you were to work directly in exponent form. So I'll show you a couple of ways. If I want to work directly from here, I'm going to do the following. And this is where I sort of mentioned about changing bases. So I'll show you one way and I'll show you another way. So I'll show you the exponent way. So in this case, this 27 can be expressed as 3 to the power of 3. And what's outside? Well, the 2 over 3. So all I did was change the base 27 into an exponent form. And the next thing we're going to do is, what do you notice here? We have a power law. So you're just going to multiply 3 times 2 divided by 3 will give me 3, and will give me 2, and then you're done. 3 squared is going to be 9. So that's one approach, directly from exponent form. But let's just say you want to work directly with a radical form. Well, for radical form, well, in this case, what BEDMAS tells you to do is exponents first, but I don't want to take 27 to the power of 2. I don't want to multiply 27 times 27. So over here, I'm going to rewrite this out as 27 in bracket the 2. So the 2 can be done later. So I'm rewriting this out in a different way. So then in this case, I deal with the brackets. Well, here goes. What's the third root or the cube root of 27? Give me a number that multiplies 23 times. That will give you 27. And that's going to be 3, you have the square, and you end up getting 9. So two different perspectives. So over here, I'll do the same thing. You end up getting, I believe, also a 9 here if you do the steps. Yes, even though there's a negative, be careful. When you take a negative and multiply it twice by itself, you end up getting a positive. All right, what about over here? If you notice here, you don't have a rational exponent, you have a decimal exponent. But decimals can be transformed into a exponent. So negative 75, 0.75 is the same thing as 16 to the power of negative 3/4. It is 3/4. And in this case, when we have negative exponents, there is many ways to make this into a radical form. You can go directly into the following. So you have 16. This is the fourth root. And I'm just going to keep it simple. Make sure that the fourth root, fifth root, they're all positive numbers. Keep it as positive. And the -3 exponent can go on the -3. Now, if you didn't want to have negative exponents, well, first things first, you can take the reciprocal and then you can change it into a radical form, which is 16, fourth root to the 3. Now, how are we going to to find the value of this? As I said, there's many different ways. So let's start directly from here. From exponent form, well, I can change the bases to 2 to the power of 4. So because 2 times 2 times 2 times 2 will give you 16, and then I use power law, I multiply the powers, I end up getting -3, and I know that I have a negative exponent, that means 1 over 2 over 3, which gives me 1 over 8. Now, if you're to work directly in radical form here, to the left, all right, now, as I said, I don't want to cube at 16. I don't want to take 16 times 16 times 16 3 times because I don't have a calculator. Keep in mind, I don't want to use a calculator. So I'm going to write this out in a different way. So 16, I'm going to put a bracket and leave that cube outside for later. So now I get to focus on this piece. So fourth root, make sure that 4 is a little 4, not a big 4. So I want the fourth root of 16, which is the same thing as 2. Then I have the little cubic, and I have 1 over 8. So there's many different approaches. I just showed you 2 of them. Now, what if you had a bracket -16 to the power of -3 over 4? How are you going to deal with this? Well, keep in mind, it really depends if you want to go through the steps, or some students will know, well, miss, you cannot take an even root of a negative number. This number doesn't exist. That's great for those students that know that rule. Let's just say you didn't know that rule. We'll go through all the motions of this. In other words, let's actually do the following. Let's actually change it directly into a radical. So in this case, we have, well, I don't want to have negative exponents. Up here, bracket -16 and 3 over 4. And then afterwards, I'm going to change it to a radical form. So here's -16. I'm going to take this fourth root, and I'm going to put a 3 outside. And then we're going to deal with this. Can you give me a number that multiplies 4 times that will give you 16? And this is where you stop, because there's absolutely no way that you can get 4 numbers that are exactly the same that'll give you a negative number. In other words, this number, this value does not exist. Now, however, if I didn't have the bracket, let's just say I had a -16, -3 over 4. Now, keep in mind, the base is not -16, it's actually 16 because there's actually -1 in front. So I like to separate that -1 away from here. And what are we left with? Well, we're left with exactly the same thing as this question, but now we're going to take our answer, which we had before was 1 over 8, and then we're going to multiply by a -1. In this case, we get -1 over 8. So just be aware of the negative brackets versus non-negative brackets. Now here we have a bit more complicated because now we have fractions and we have a radical form. So we're actually working backwards right now. So working backwards is the following. So here is our entire base. So I'm going to put here in brackets -125 over 27. The question right now is what goes here and what goes here. Now keep in mind the 3 tells you the type of root. So in the denominator is going to be 3. But if you notice here, there is no exponents outside. In this case, if there's no exponent, it's automatically a 1. This one over here, we can put in brackets, that massive fraction over there. And we know that we have a numerator and a denominator. The 5 tells you the type of root, which is the fifth root. And over here, we have a -2. Now, the next thing it says, evaluate. It never says to use a calculator or not a calculator. So if you can use a calculator, that's great. But let's just say you didn't have a calculator. This is where I believe changing bases is also very important. In other words, you have to know your multiplication skills. 125, I know that it's -5 over 27 to the power, I know that 125 is the same thing as 5 times 5 times 5 is 3 times. 27 is 3 times 3 times 3, 3 times. In other words, this is the base. And I put another square bracket, this fraction outside. So in other words, I'm going to actually keep the brackets, and then I'm going to multiply these two together, because using power law, 3 times a third is just 1, and we're left with -5 over 3. Anything to the power of 1 doesn't really change the base. This is only good if you're comfortable with your multiplication skills. Otherwise, you'll probably have to use your calculator. Same thing for here. Over here, if I were to do this by hand without the calculator, I would have to know something about 32, which I do know, which is the same thing as 2 to the power of 5. This one here is the same thing as 3 to the power of 5. And everything here is negative 2 over 5. Now over here, I'm doing something unconventional, meaning, well, I wouldn't say unconventional, just something a little bit slightly off. So I'm going to use the power law. Now keep in mind, this power here applies to all the exponents, both top and bottom. In other words, the base is still 2 and 3, but the exponent is going to change. So over here, you're going to have to multiply the fraction, which gives you negative 2. Over here, you're going to have to multiply the fraction, which also gives you negative 2. And I think I made this question more difficult than it is, but it's okay. It's a different approach. In this case, I know that this becomes 1 over 2 squared divided by 1 over 3 squared, because I like to put things horizontally rather than vertically. This becomes 1 over 4 divided by 1 over 9, and we know that to multiply fractions, if we take the reciprocal, end up getting 9 over 4. As I said, what I did here is unconventional. There's other ways to do this, probably more faster. You can actually go try it. So here we have the last example. It looks a little bit more complicated, but it's really not. So it says here express as a single power. Single power means your answer should be the following: a base, an exponent, and nothing else. So how are we going to combine everything together? Well, if you notice, in every single part, there is a number 8. So what we can do is change everything into a base exponent. The first part is done. 8 to the 5 over 6 times, how can we change this into an exponent form? Well, keep in mind this is a square root. In other words, we have a 2 at the denominator of the rational exponent and a 1 because there's a 1 on the 8. Over, do the exact same thing. 8 to the power of, we know that this is the third root and this is the fifth to the power of 5, sorry. And after that, it's all exponential laws. So in this case, what happens when you multiply same bases? Well, you're going to take 5 over 6 exponents and add them together. And what happens if you divide same bases? You still have the exponent. Please do not slash them out. It is not 1. All right. It is still at 8. And what do you do with the exponents? You're going to subtract. In other words, 5 over 6 plus 1 over 2 minus 5 over 3, and then you're done. I'm not going to spend time simplifying this. You can do this on your own. So you end up getting a fraction, I think, at the end.